The night sky may seem serene, but the universe is a vast, chaotic abyss, far more terrifying than we dare to imagine. It is ruthless, unpredictable, and filled with objects that would rip you apart if you get too close. But we cannot stay home forever. Our curiosity about the unknown drives us to leave Earth and explore the cosmos. At first, this journey seemed harmless. We started with our neighboring planets. We found Mars. We found Venus. We stepped on the Moon, thinking that these celestial bodies were just cold, barren landscapes. But as we studied them further, we realized their dangers. We found Venus with its crushing atmosphere of sulfuric acid and temperatures hot enough to melt lead, and Mars with its dust storms that could envelop the entire planet. We found these planets were anything but friendly. Then in the 20th century, we moved beyond our planetary neighbors. We discovered asteroids. We discovered comets. We learned that a single collision with one of these could end life as we know it, just like it did with the dinosaurs millions of years ago. But we still kept pushing further. We still kept going far and far away into the cosmos, into the darkest of its secrets. Then we found black holes, regions of space so dense that nothing, not even light, can escape. But we did not stop, even if we were skinned.
Let's start with the basic building blocks of everything we know. At the smallest scale, everything around us is made up of particles, tiny bits that join together to form the matter we see and interact with every day. But these particles aren't like little marbles or solid balls. They don't even have a specific shape, and they certainly don't behave in ways we're used to. To understand this, let's break down what a particle really is in the quantum world. Particles, like electrons and photons, are not just single points. In fact, the very idea of a particle in quantum mechanics is a bit misleading. It's better to think of particles as tiny, wave-like disturbances in something called a quantum field. Quantum fields are spread out across the entire universe, like invisible, flowing webs that cover every inch of space. Each type of particle has its own unique field. For instance, the electron field is responsible for creating electrons, while the photon field gives rise to photons, which are the particles of light. When we detect a particle, what we're really seeing is an energy blip or a disturbance in that field. Imagine dropping a pebble in a pond. The ripples that form are like the appearance of a particle in a quantum field. These particles show up as little waves, moving through the field with specific properties like charge or mass. But here's the strange part. Unlike the ripples on a pond, these quantum ripples can behave in ways that seem to break the rules of common sense. Particles like electrons, for example, can be in more than one place at the same time. This phenomenon is known as superposition. Think of it as the ability of a particle to exist in multiple locations simultaneously, like a shadow spread across several places at once. In everyday life, we would never see something like this happen, but in the quantum world, it's normal. Only when we look or measure the particle does it choose one specific place to be. Now, let's talk about another strange quality of particles. They don't have a fixed path. When a particle moves from one point to another, it doesn't travel in a straight line like we might expect. Instead, it can take multiple paths, behaving more like a wave spreading out over all possibilities before settling on one path when observed. This property is fundamental to quantum mechanics and is part of what makes it so unique and challenging to understand. At this level, there are no clear-cut paths, only probabilities. A particle might be more likely to be in one place than another, but we can't say for certain until we measure it. Alongside particles, these fields also play a critical role in shaping our universe. Fields are like invisible forces that fill up space, even if we can't directly see or feel them. They're the canvas on which particles appear and interact, forming everything from atoms and molecules to the planets and stars. The interactions between these fields are what give rise to the fundamental forces of nature, like electromagnetism, which causes magnets to attract or repel each other, or gravity, which holds planets in orbit around stars. Let's look at one field we're all familiar with, the electromagnetic field. This field is present everywhere, and it's responsible for light, electricity, and magnetism. When the electromagnetic field vibrates in a certain way, it creates photons, the particles that make up light. Every time you turn on a light, you're essentially creating countless photons by disturbing the electromagnetic field in just the right way. These photons then travel through space, hitting your eyes and allowing you to see. Then we have other fields, like the electron field, which produces electrons, the particles that carry electric charge and are essential in forming atoms. In fact, electrons are part of what gives atoms their structure. They orbit around the nucleus, which is made up of other particles like protons and neutrons. Protons and neutrons themselves are made from particles called quarks, which interact through yet another field called the strong field. The strong field holds quarks together inside protons and neutrons, giving stability to the nucleus of an atom. All these fields, from the electron field to the electromagnetic field, are part of what scientists call quantum field theory. This theory helps explain how particles and forces interact at the smallest scales. Unlike classical theories that see particles as solid objects, quantum field theory shows that particles are just temporary ripples in these fields. They can appear and disappear depending on the conditions, and they behave more like waves than anything solid. An interesting thing to note is that these fields don't just exist in some far-off space. They're all around us, constantly creating and changing particles. In fact, the space you're sitting in right now is filled with these fields, even if you can't feel them directly. Every single particle we observe, touch, or see comes from some interaction within these fields. The table in front of you, the screen you're looking at, and even your body are made up of particles born from these invisible fields. They are the fundamental framework that creates the matter and energy we experience. But quantum fields don't just create particles. They also allow particles to interact with one another. When two particles meet, they exchange energy and information through these fields. For example, when an electron interacts with a proton, they exchange photons within the electromagnetic field. This exchange creates the force that keeps electrons orbiting around atomic nuclei, forming the atoms that build up everything we know. This simple exchange process is happening constantly, holding atoms together and allowing molecules to form. So, in a way, particles and fields are two sides of the same coin. Particles are just the observable outcomes, while fields are the deeper, unseen forces at work. This is one of the most mind-opening ideas in quantum mechanics, the notion that particles are not isolated objects, but rather expressions of underlying fields that fill up all of space. As we continue exploring quantum mechanics, we'll see that these fields, particles, and their strange behaviors lay the groundwork for even deeper mysteries. The universe is far more interconnected and fluid than it appears, and it's through quantum particles and fields that we start to glimpse the complex underlying structure that holds everything together. Now, let's dive into a part of quantum mechanics that is both puzzling and essential, the concept of the quantum vacuum, and zero-point energy. These ideas might sound complex, but they're actually about understanding what empty space really means. When we think of a vacuum, we usually imagine an area that has nothing in it. No air, no particles, just pure emptiness. But in quantum mechanics, even empty space is far from being truly empty. It's actually full of activity and energy. To start with, think of the quantum vacuum as the space between particles. Even in what we think of as empty space, quantum fields still exist. These fields are always there, stretching across the entire universe. In the vacuum, these fields are not actively creating visible particles, but they are still present, always ready to create particles if the right conditions arise. And because of this readiness, the vacuum isn't silent or calm. Instead, it's filled with tiny fluctuations and bursts of energy that occur at a very small scale. This constant background energy is what scientists call zero-point energy. Zero-point energy is named this way because it's the lowest energy state that a quantum system can have. It's called zero point because even if we remove every particle and lower the temperature as much as possible, this energy still exists. Unlike in classical physics, where we think energy can be removed completely, zero-point energy is the unavoidable, baseline energy of any quantum field. It's like the minimum energy level that nature allows a field to have. To understand how zero-point energy works, let's imagine a small field within the vacuum of space. Even when it seems like there's nothing in this space, the quantum field within it is still fluctuating. These fluctuations come from the fact that particles and fields in quantum mechanics are never truly at rest. They're always moving or wiggling a tiny bit, even at the lowest energy level. This motion is random, creating tiny, brief appearances of particles and antiparticles that pop in and out of existence before we can observe them. These tiny particles don't last long enough to be detected directly, but their effects can be observed through the energy they produce. One interesting example of zero-point energy in action is something called the Casimir effect. If you place two very flat metal plates close together in a vacuum, you'll find that they start to pull toward each other. This attraction happens because the zero-point energy between the plates is slightly less than the energy outside them. The quantum vacuum exerts a small force on these plates, causing them to move closer together. This force is weak and only noticeable at extremely small distances, but it's a clear demonstration of zero-point energy. The plates behave as if there's a kind of pressure pushing them together, even though they're in a vacuum with no particles or heat involved. It's also worth noting that the quantum vacuum and zero-point energy are not visible or detectable in the way we might observe a photon or an electron. Instead, we infer their existence from their effects on physical objects. In this sense, zero-point energy is like an invisible force that subtly influences the behavior of matter and energy in the universe. Scientists use careful measurements and experiments to understand these effects and develop theories that explain how the quantum vacuum works. Another interesting idea connected to zero-point energy is the concept of virtual particles. In a quantum field, energy can briefly turn into particles and then disappear again. These are called virtual particles because they don't last long enough to become real particles that we can observe directly. However, they can still interact with other particles, creating tiny, momentary effects. For instance, virtual particles play a role in the forces that particles exert on each other, like the attraction between two charged particles. Even though we can't see them, virtual particles help make sense of how quantum fields behave, especially in what we think of as empty space. It might seem strange to think of particles popping in and out of existence, but in quantum mechanics, this is normal. Virtual particles are not like regular particles that we can see or measure directly. They're more like brief disturbances or waves within a field. They only appear for a moment before disappearing again, leaving behind slight changes in energy that scientists can measure. These tiny fluctuations are part of the natural state of the quantum vacuum and are one of the reasons why zero-point energy exists. To go a bit further, zero-point energy and the quantum vacuum have implications for how particles and fields interact with each other. Even though we can't directly see zero-point energy, it affects the way particles move and behave. For example, zero-point energy influences the ground state of atoms, meaning it plays a role in how electrons orbit the nucleus of an atom. Because electrons are never fully at rest, they vibrate even at absolute zero temperature due to zero-point energy. This slight vibration is a result of the constant fluctuations of the quantum vacuum, which affect every particle even when we think it's still. Finally, it's important to understand that zero-point energy and the quantum vacuum are everywhere. No matter where you go in the universe, these tiny fluctuations and virtual particles are present. Space isn't just a passive background. It has an active, restless energy at all times. This idea changes how we think about space and energy. Rather than a calm, empty backdrop, the vacuum is more like an endless sea of activity, with fields always shifting, even when we think nothing is happening. Entanglement is one of the most mysterious aspects of quantum mechanics, showing us that particles can be connected in ways that seem to defy ordinary logic. When two particles become entangled, they form a kind of link that connects them, even if they're separated by vast distances. What happens to one particle will immediately affect the other, no matter how far apart they are. This connection doesn't fade with distance. The entangled particles remain linked, whether they're a few inches apart or across the galaxy. To get a clear picture, let's imagine two particles created in the same process, like a pair of twins. From the moment they're created, they are entangled, meaning they share a special connection that lets them know each other's state. For example, if one particle spins a certain way, the other particle's spin will automatically adjust to match. This might sound simple, but the strange part is that this knowing happens instantly. If you measure the spin of one particle and find it spinning in a particular direction, the other particle will be found spinning in the opposite direction. This result is guaranteed, even though the particles are far apart. What makes entanglement unique is that there's no way for one particle to send information to the other because, in a sense, they're already sharing the same information. It's as if the particles don't act like separate objects anymore. They behave as if they're part of the same system, no matter how far apart they are. This instant connection seems to go against our usual ideas of how information should travel, especially since nothing in our everyday world behaves this way. In classical physics, information can only travel as fast as the speed of light, which is the fastest speed possible. But in the case of entangled particles, the effect seems to happen immediately, with no delay at all. This instant change has led some scientists to describe entanglement as non-local, meaning it doesn't follow the usual rules about location or distance. Once particles are entangled, they behave as if they're a single entity spread across space, ignoring the usual boundaries that separate them. The concept of entanglement became widely known due to a famous debate between Albert Einstein and other physicists. Einstein found the idea troubling and called it spooky action at a distance because it didn't fit with his understanding of how the universe should work. He believed that there had to be some hidden information or variables that we couldn't see, which could explain why entangled particles seem to know each other's state. However, experiments over time have shown that there are no hidden variables at work. The entanglement link is real, even if we don't fully understand why it works this way. The way entanglement is created is also interesting. When two particles interact in specific ways, they can become entangled. For instance, if two particles are created from the same source or experience certain interactions together, they can become linked in a way that entangles their properties. Once this entanglement happens, measuring a property of one particle will instantly affect the other particle. It's like they have a permanent connection that can't be broken, even if they are separated by large distances. Entanglement isn't limited to small particles like electrons or photons. Scientists have managed to create entangled states with larger groups of particles, although the effect becomes harder to maintain as the system grows. This is because entanglement is a delicate state. If an entangled particle interacts with something else, its entanglement can break or become weaker. This fragility is part of what makes entanglement hard to study and work with, especially in practical applications. One of the interesting aspects of entanglement is that it doesn't allow for faster-than-light communication. Even though the effects of entanglement appear instantly, there's no way to use it to send information or signals across distances. For instance, if you try to use entangled particles to send a message, you would still need to transmit information through regular means, which are limited by the speed of light. Entanglement allows a correlation between particles, but it doesn't allow us to control the outcomes in a way that could carry messages. In research labs, scientists use entanglement in experiments to learn more about the nature of quantum mechanics. Entangled particles are used in certain technologies, like quantum cryptography, which allows for highly secure communication by making use of the properties of entanglement. When two people share entangled particles, any attempt by a third party to intercept or tamper with the particles would break the entanglement. This tampering would be instantly detectable, making quantum cryptography one of the most secure forms of communication. Entanglement also plays a role in the field of quantum computing. In a quantum computer, particles are used as qubits, which can hold and process information. When these qubits are entangled, they can work together in ways that allow for faster and more complex calculations than a regular computer can manage. By using entanglement, a quantum computer can perform many calculations at once, solving certain problems much faster than a traditional computer. However, despite these applications, entanglement itself remains mysterious. The exact reason why particles behave this way is still unknown, and there isn't a full explanation for why entanglement works. It's one of the fundamental puzzles of quantum mechanics, an example of how particles in this realm follow rules that don't make sense in our everyday world. The uncertainty principle is one of the most fundamental ideas in quantum mechanics. It tells us there are limits to what we can know about particles and their behavior. Unlike in classical physics, where we can measure things like position and speed very accurately, the uncertainty principle shows that, at the quantum level, there are strict limits on our ability to make precise measurements. Let's break down what this principle really means. Imagine you have a particle, like an electron. In classical physics, we could measure both its exact position and its exact speed or momentum without any trouble. But in quantum mechanics, if you try to measure the electron's position very accurately, you won't be able to know its momentum with the same level of precision, and vice versa. This is not because of any flaw in our measuring tools. Instead, it's a built-in feature of how quantum particles behave. The uncertainty principle was first introduced by physicist Werner Heisenberg, so it's sometimes called Heisenberg's uncertainty principle. According to this principle, the more accurately you try to measure one property of a particle, like its position, the less accurately you can know another property, like its momentum. This is because particles at the quantum level don't have definite positions and momentum in the way we're used to with larger objects. Instead, they exist in states that are described by probabilities. To understand this better, think of a particle as having a cloud of possible positions and a separate cloud of possible momenta, the product of mass and velocity. These clouds represent where the particle might be and how fast it might be moving, but they're not exact. The uncertainty principle states that these clouds can't both be sharply defined at the same time. If you try to shrink the position cloud down to a precise spot, the momentum cloud expands, making it impossible to know the momentum accurately. One way to think about this is by imagining a camera trying to capture a picture of a moving object in dim light. If you increase the camera's exposure time to get a clear picture of the object's position, the motion might make the picture blurry, losing details about the object's speed or direction. Conversely, if you shorten the exposure to capture the movement more accurately, you lose details about its exact position. The uncertainty principle works in a similar way, but it's a fundamental property of quantum particles, not an issue with measurement tools. This principle applies to more than just position and momentum. It affects other pairs of properties as well, such as energy and time. If you try to measure the energy of a particle very precisely, you can't know the exact time when it had that energy. This relationship between energy and time also stems from the uncertainty principle and adds to the challenges in studying particles at the quantum level. The uncertainty principle tells us that there's a natural fuzziness to particles at this scale. When we think of particles, we usually imagine them as tiny points moving along defined paths. But in quantum mechanics, particles don't move in the same way. They exist in a range of possible locations and states, and the uncertainty principle is a direct result of this probabilistic nature. The position of a particle is not just unknown in the traditional sense, it simply doesn't have an exact position until we measure it. When we do, we change the state of the particle, affecting its momentum or other properties. An experiment that demonstrates the uncertainty principle involves firing electrons through two slits in a screen. When you try to observe which slit each electron passes through, the electrons act like particles, moving in straight lines. But when you don't observe their paths, they behave more like waves, creating an interference pattern that suggests they passed through both slits at once. This experiment, known as the double-slit experiment, shows that particles can behave as waves, and that measuring certain properties affects their behavior in ways that reveal the uncertainty principle at work. Because of the uncertainty principle, quantum mechanics relies on probabilities rather than exact values. Instead of saying a particle is here or there with absolute certainty, quantum mechanics tells us the likelihood of finding a particle in a certain location or state. This approach is different from the certainty we expect in classical physics, where objects follow clear paths and patterns. In the quantum world, we can only predict the odds of a particle's behavior, not its exact position or momentum at any given time. The uncertainty principle also influences the energy levels within atoms. Electrons in an atom don't have fixed orbits like planets around the sun. Instead, they occupy regions called orbitals, where there's a high probability of finding an electron. The uncertainty in the electron's position and momentum means it can never be completely still. Even at absolute zero temperature, where we might expect all motion to stop, the uncertainty principle ensures that there is still a minimal amount of motion. This is part of what we discussed earlier as zero-point energy, the lowest possible energy that particles can have. Interestingly, The uncertainty principle prevents certain situations that would seem possible in classical physics. For instance, because of this principle, an electron can't simply fall into the nucleus of an atom and stay there. If it did, we would know both its exact position in the nucleus and its exact momentum, 0, because it would be still. The uncertainty principle prevents this scenario, keeping electrons in motion and allowing atoms to have stable structures. In the quantum world, there's always a balance of sorts, where knowing more about one property means knowing less about another. This limitation changes the way we understand particles and their interactions. Rather than tracking exact positions and movements, we work with probabilities and ranges, which reflect the reality of quantum behavior. The uncertainty principle reminds us that at the quantum level, our knowledge is always partial and limited, not by our tools, but by the very nature of quantum particles themselves. This principle is one of the defining features of quantum mechanics, setting it apart from classical physics and showing us that at the smallest scales, nature has its own set of rules that sometimes defy our expectations. One of the strangest ideas in quantum mechanics is superposition. In simple terms, superposition means that a particle, like an electron, can exist in multiple states or positions at the same time. This idea is hard to grasp because, in our everyday experience, objects are only in one place or one state at a time. But in the quantum world, particles don't follow these familiar rules. To picture this, imagine a coin. When you flip it, the coin is either heads or tails when it lands. But in a quantum sense, until it's observed, the coin could be considered to be in both states, both heads and tails at the same time. Only when you look at it does it choose one outcome. Quantum particles act like this. They exist in a blend, or superposition, of all possible states until they're observed. This concept was famously illustrated in a thought experiment by physicist Erwin Schrödinger called Schrödinger's cat. In this scenario, a cat is placed in a box with a mechanism that has a 50-50 chance of releasing poison, depending on a quantum event, like a particle decaying, until the box is opened and someone observes the cat. It can be considered both alive and dead at the same time, because the quantum event that controls the poison hasn't been observed yet. This paradox shows the strange nature of superposition, where the cat state is linked to the uncertain state of the particle. In reality, particles like electrons or photons don't decide their state based on classical logic. Instead, they exist in a probability cloud, a range of possible locations or conditions. This probability cloud represents all the possible states a particle could be in. When we try to measure or observe the particle, we interact with it, and it chooses one state. This collapse of the superposition into one outcome is part of what defines quantum mechanics. Superposition is not just a theoretical idea. It has been observed in experiments. For example, scientists can place particles in a superposition of two paths. Imagine an electron being fired toward a screen with two slits. The electron can pass through both slits at once in a superposition, creating an interference pattern on the screen as if it were a wave. However, if we measure the electron's path, the superposition collapses, and the electron appears to take only one of the two paths. In quantum mechanics, superposition is described using a mathematical tool called a wave function. The wave function captures all the possible states of a particle and their probabilities. For example, if an electron's position is uncertain, its wave function will show a range of possible locations. Until we measure the electron, it exists in all these positions at once. The wave function gives a probability for each possible position, telling us where we're most likely to find the electron if we make a measurement. One of the key differences between quantum and classical physics is how particles behave when they're not observed. In classical physics, if we can't see an object, we still assume it's in one place. But in quantum physics, a particle that isn't observed doesn't have a definite position or state. It exists in a superposition of many possibilities. Only when we interact with it or measure it does it settle into one of those possibilities. This behavior is why quantum mechanics uses probabilities rather than certainties. Superposition also plays a big role in quantum computing. Unlike traditional computers, which use bits as the smallest units of data, quantum computers use qubits. A classical bit can be in one of two states, 0 or 1. A qubit, however, can be in a superposition of both 0 and 1 at the same time. This allows quantum computers to process many possible outcomes simultaneously, making them incredibly powerful for certain types of calculations, like factoring large numbers or simulating molecules for drug discovery. To illustrate, think of a classical bit as a switch that's either on or off. A qubit, on the other hand, is like a spinning coin. It's in a blend of on and off until you measure it. This ability to exist in multiple states allows quantum computers to perform complex calculations much faster than traditional computers. Superposition is what makes qubits so unique and gives quantum computers their potential for solving problems that are too difficult for classical computers. Another example of superposition in action is in quantum cryptography. Quantum cryptography uses the principles of quantum mechanics to create secure communication channels. If someone tries to intercept the message, they would have to measure the qubits used to encode the information. But measuring a qubit collapses its superposition, changing its state. This means any eavesdropping attempt would be detected, as the state of the qubits would no longer match. This feature makes quantum cryptography highly secure, as it relies on the principles of quantum mechanics, not just complex mathematical codes. Experiments have also shown superposition with larger objects, although it's much harder to observe than with tiny particles. Researchers have been able to put molecules made of many atoms into superposition states, showing that even larger particles can exhibit quantum behavior. However, as objects get bigger, superposition becomes harder to maintain. This is because large objects interact more with their surroundings, which measures them in a way, causing their superposition to collapse. This process of losing superposition due to interactions with the environment is called decoherence. In a sense, decoherence is why we don't see superposition in our everyday lives. Objects we interact with are constantly measured by their environment, whether through light, air molecules, or other forces. This constant interaction collapses any superposition that might exist, making objects behave in the predictable ways we're used to. Imagine a huge, invisible field spread all over the universe, like a mist that touches everything, everywhere. This invisible field is called the Higgs field, and it's responsible for giving particles mass. But why do particles need this field to gain mass? To understand, let's break it down step by step. First, what is mass? Mass is what makes particles feel heavy or light. It's why lifting a rock is harder than lifting a feather. But at the fundamental level, particles like electrons or quarks don't come with mass on their own. Without an external process, they wouldn't interact the way they do to form atoms, molecules, and ultimately the world around us. Here's where the Higgs field comes in. This field was the missing link that explained why some particles, like electrons, have mass, while others, like photons, particles of light, don't. But there was no direct evidence of it for decades. It was just an idea, a big what if. That is, until the Higgs boson was discovered in 2012. So, what exactly is the Higgs boson? To picture it, imagine ripples or waves on a pond. If you throw a stone in the water, it creates ripples. The Higgs boson is like one of those ripples in the Higgs field. It's a particle created when this field is disturbed or excited by energy. Scientists built the Large Hadron Collider, huge particle collider, specifically to find evidence of this Higgs boson, proving that the Higgs field exists. Now, let's take a closer look at how particles gain mass through this field. Think of the Higgs field like a crowd at a party. When a particle moves through this crowd, it interacts with it. Some particles move easily through the crowd, like people weaving smoothly in and out. These particles interact very little with the Higgs field and therefore have very little mass. Others get stuck or slowed down by the crowd, making it harder for them to move through. These particles interact a lot with the Higgs field and, as a result, gain more mass. Electrons, for example, interact with the Higgs field, so they gain mass. But photons, the particles of light, do not interact with this field at all, which is why they have no mass and can travel at the speed of light. This interaction with the Higgs field decides how massive or light a particle becomes. Now you might wonder, why does it matter that particles have mass? Well, this is important because mass is a property that allows particles to come together to form atoms. Atoms, in turn, form molecules, and molecules build everything in the universe. Without mass, particles would fly around without forming any structures, and the universe would be just a sea of energy, with no stars, planets, or even life. This makes the Higgs field a central part of why the universe looks and behaves the way it does. Back in 2012, the discovery of the Higgs boson was celebrated worldwide. Scientists used the Large Hadron Collider, located at CERN near Geneva, Switzerland. The LHC is a massive circular tunnel where particles are smashed together at nearly the speed of light. By observing these collisions, scientists detected evidence of the Higgs boson, the particle that proves the Higgs field exists. It took years of data analysis to confirm this particle, and when they did, it was a massive leap forward in our understanding of physics. The discovery of the Higgs boson confirmed a major part of the standard model of particle physics. The standard model is like a detailed map of all the fundamental particles and forces in the universe, describing how they interact with each other. However, without the Higgs boson, the standard model would not be able to explain why particles have mass. The discovery showed that the theory was correct, at least for the particles and forces we know. However, it also left open many questions, especially about forces we still don't fully understand, like gravity. The Higgs field itself is everywhere, filling the entire universe. It doesn't have a direction or flow. It's just present in all of space. When particles move through it, they gain mass based on how much they interact with this field. This interaction is unique for each type of particle, giving each particle a different mass. To understand the beginning of the universe, we have to go back to a time when everything was incredibly small and packed together, so small, in fact, that quantum mechanics becomes crucial to describing what was happening. Quantum mechanics is the science that explains the behavior of tiny particles, like atoms and the particles inside them. When the universe was just beginning, It was in a state we call a quantum state, where normal ideas of time and space start to break down. Let's start with the Big Bang. The Big Bang theory suggests that the universe began from a point of infinite density and heat around 13.8 billion years ago. In those early moments, the universe was much smaller than an atom, an extremely hot and dense place where the laws of physics as we know them didn't yet work in the usual way. Instead, quantum laws took over. Instead of thinking about particles as tiny points, we think of them as waves or fields that are constantly changing. Quantum mechanics describes these behaviors, including the strange ability for particles to pop in and out of existence, move through barriers, and act in ways that don't make sense in our everyday world. One of the key ideas in quantum cosmology is quantum fluctuations. These are tiny, random changes that happen because of quantum uncertainty. In the very early universe, before it even began to expand, these fluctuations were happening all the time. Even in empty space, particles and energy can appear and disappear, a result of quantum uncertainty. These fluctuations created tiny differences in density that eventually became the seeds for galaxies and clusters of galaxies as the universe expanded. So, even though these fluctuations were incredibly small, they had a huge impact on how the universe looks today. Right after the Big Bang, the universe started expanding very quickly in a period we call inflation. During inflation, the universe expanded at an enormous rate, much faster than we see today. This inflation stretched out the tiny quantum fluctuations, making them much larger. This process created the initial structure of the universe, which later grew into galaxies and stars. Without these fluctuations, the matter in the universe would likely have been spread out evenly, and galaxies, stars, and planets would not have formed. Inflation took place very early on, possibly in the first tiny fraction of a second after the Big Bang. Quantum mechanics played a major role in shaping this phase of the universe's history. Another aspect of quantum cosmology is how time and space themselves were affected. In classical physics, time and space are fixed backgrounds where events happen. But in quantum cosmology, time and space are dynamic. They change and are affected by the particles and fields within them. Early on, when everything was at incredibly small scales, time and space may have behaved very differently. For instance, time may not have flowed the way we experience it now. Some theories suggest that before the Big Bang, time didn't exist in the way we understand it. Instead, there was a kind of quantum fog where typical ideas of past, present, and future don't apply. Quantum cosmology also raises the idea that our universe could be one of many. Some theories suggest that in the quantum world, different outcomes can create separate paths or realities, sometimes called multiverses. This means that our universe could be just one version of reality that emerged from the quantum state, with other versions leading to different kinds of universes. In some interpretations, every quantum possibility could spawn its own universe, creating an endless variety of possible worlds. The study of quantum cosmology aims to bridge two big theories: quantum mechanics and general relativity. Quantum mechanics explains the behavior of very small particles, while general relativity explains how large objects like planets, stars, and galaxies move and how gravity works. But when we try to combine these two theories to describe the universe's very beginning, they don't work well together. General relativity doesn't include quantum effects, and quantum mechanics doesn't include gravity. Scientists believe that understanding quantum cosmology could lead to a theory that combines these two, something often called quantum gravity. This unified theory could explain what really happened at the start of the universe and how the laws of physics came to be. One approach to this is the idea that the universe began not from a single point, as in the traditional Big Bang, but from a quantum wave function. The wave function is a mathematical description that represents all the possible states of a quantum system. In this view, the universe itself could be described as a giant wave function that contains all possible histories of how the universe could have evolved. This idea, known as the wave function of the universe, was developed by scientists trying to use quantum principles to explain the cosmos. Understanding quantum beginnings might also tell us why the universe has certain properties, like why it's expanding at the rate it is, or why certain particles have the masses they do. These properties are finely tuned to allow life and structure to exist, and quantum cosmology may reveal why this fine-tuning happened the way it did. While the early universe was chaotic and strange, it also followed certain patterns and rules that ultimately led to the formation of stars, galaxies, and even planets capable of supporting life. Quantum cosmology remains a challenging and often theoretical field, as we can't go back in time to directly observe the early universe. Instead, scientists rely on experiments, mathematics, and simulations to explore these questions. The study of cosmic microwave background radiation, which is a faint glow left over from the early universe, provides some clues. This radiation gives us a snapshot of the universe as it was about 380,000 years after the Big Bang, showing the imprint of those quantum fluctuations that seeded galaxies. The universe has many mysteries, and two of the biggest are dark matter and dark energy. Even though they make up most of the universe, we still don't fully know what they are. Dark matter and dark energy don't interact with light, which is why they're called dark. Let's dive into what we know and explore some ideas about their possible quantum connections. Dark matter is the first mystery. Imagine looking at a galaxy. It's made up of stars, gas, and dust, all held together by gravity. But when scientists looked at galaxies closely, they found a problem. Based on how much visible matter there is, galaxies should not be able to hold together. There isn't enough visible mass to create the gravity needed to keep everything from drifting apart. This led scientists to think there must be more stuff out there that we can't see. This unseen matter is called dark matter. Scientists think dark matter might be made of particles, just like regular matter. However, these particles don't seem to interact with light or any electromagnetic force, which is why they're invisible to us. Since they don't emit or reflect light, they only reveal themselves through gravity. Many theories try to explain what dark matter could be made of. Some suggest it's made up of particles called WIMPs, weakly interacting massive particles. These are particles that could be floating all around us, but don't interact with normal matter except through gravity. Another idea is that dark matter could be made of particles called axions, which are even lighter than WIMPs. Axions, if they exist, might have quantum properties that allow them to fill space in a smooth way, almost like a field, rather than clumping together like regular particles. This could explain why dark matter seems to be spread evenly around galaxies, creating a kind of halo that holds everything together. Now, let's talk about dark energy. This is an even stranger mystery. Scientists discovered that the universe isn't just expanding, it's expanding faster and faster. This was unexpected because gravity should be slowing down the expansion, or at least keeping it steady. But something is pushing galaxies away from each other, as if there's an invisible force acting against gravity. This force is called dark energy. One explanation for dark energy is that it could be linked to something called the cosmological constant. This idea was first suggested by Albert Einstein as a way to balance the universe and keep it stable. Later, he discarded it, but it came back when scientists realized the universe's expansion was accelerating. The cosmological constant suggests that empty space itself has energy, sometimes called vacuum energy, and that this energy could be causing the universe to expand faster. Quantum physics has a role here because, according to quantum mechanics, even empty space is not truly empty. It has tiny, random fluctuations, with particles popping in and out of existence. This vacuum energy from empty space might explain dark energy. There's a big problem, though, known as the cosmological constant problem. When scientists try to calculate the amount of vacuum energy using quantum theory, the number they get is way too large, about 120 orders of magnitude larger than the dark energy we actually observe. This is a huge difference, and no one knows why. Some scientists think there's something in quantum theory or gravity we still don't fully understand. There are also some ideas that connect dark energy and dark matter in unique ways. One idea is that dark matter might have a quantum connection to dark energy. Some theories suggest that dark matter particles could interact with each other in a way that creates something similar to dark energy. These particles would not interact with regular matter, so we wouldn't notice them directly. But their interactions could create a small, continuous energy in space, which might look like dark energy on large scales. Some scientists are even exploring the possibility that dark matter and dark energy are not separate things, but different effects of a single underlying force or field. This idea is called unified dark energy and dark matter models. In this view, dark matter would act like regular matter on small scales, helping galaxies stay together. On larger scales, it could have properties similar to dark energy, pushing galaxies apart and accelerating the universe's expansion. Quantum theories try to explain dark matter and dark energy in other creative ways too. One interesting idea is that dark matter might exist in a quantum superposition across the universe. Superposition is a property in quantum mechanics where particles can exist in multiple states at once. If dark matter has this property, it could be spread out over vast distances without clumping in the way ordinary matter does. This superposition would make dark matter harder to detect, but might explain why it acts differently from visible matter. Another quantum-based theory is the idea of quantum fields. In quantum mechanics, particles are seen as excitations or ripples in fields that fill space. For instance, photons are ripples in the electromagnetic field. Some scientists think there could be special fields for dark matter and dark energy. These fields would be present throughout the universe, but would only interact through gravity, which could explain why we don't see dark matter and dark energy directly. One theory, called modified gravity theories, suggests that dark energy could result from changes to our understanding of gravity itself. In these theories, gravity might work differently on very large scales than it does on small scales, meaning the force that pulls objects together could be weaker on the scale of galaxies and stronger on smaller scales. If gravity behaves differently in large parts of the universe, it could give the appearance of a force like dark energy, even though it's really just gravity acting in an unexpected way. Experiments are underway to search for dark matter particles. Some of these experiments involve particle detectors buried deep underground to avoid interference from other particles. These detectors are designed to capture a rare interaction between dark matter particles and regular matter. Other experiments use particle accelerators, like the Large Hadron Collider, to try to create dark matter particles in high-energy collisions. Scientists are also looking at ways to understand dark energy better. By observing the light from distant galaxies and supernovae, they can measure how the universe's expansion changes over time. These observations help us understand dark energy's role in the cosmos. Quantum mechanics usually describes the tiniest parts of nature, particles much smaller than atoms. At this level, things don't behave in ways we might expect. Particles act more like waves than solid points. They can even appear in places they shouldn't be able to reach or flicker in and out of existence. While we tend to think of these behaviors as something only visible under microscopes, some scientists believe that quantum effects can actually have an impact on much larger scales, even across the vastness of space. One of the most intriguing examples of quantum weirdness on a cosmic level involves black holes. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. But when we look at black holes through the lens of quantum mechanics, we find that they're not as simple as just dark holes. One strange quantum effect near black holes is called Hawking radiation. Named after physicist Stephen Hawking, this idea suggests that black holes can slowly lose mass by giving off tiny particles, even in what seems like empty space around them. These particles are thought to come from the random, popping behavior of particles in the vacuum around the black hole, a result of quantum fluctuations. Quantum fluctuations are another form of cosmic scale weirdness. Even in empty space, where we think there's nothing, quantum theory tells us that particles and energy are constantly appearing and disappearing. These random fluctuations don't usually affect our daily lives, but in the vast, empty spaces between galaxies, these tiny fluctuations can add up. Some scientists believe that these fluctuations could play a role in the universe's structure, possibly affecting how galaxies form or even helping to shape the universe's large-scale structure. In addition to black holes, wormholes are another place where quantum mechanics and cosmic scales may meet. Wormholes are hypothetical passages through spacetime, sometimes thought of as shortcuts between distant points in the universe. If wormholes exist, they might be affected by quantum rules. Some theories suggest that if a wormhole were small enough, quantum effects could prevent it from staying open, making it collapse quickly. However, if we could somehow stabilize a wormhole with quantum fields or particles, it could theoretically become a bridge between two parts of space. The challenge is that we've never actually observed a wormhole, but the math hints at a link between quantum mechanics and these potential cosmic passages. Quantum mechanics also changes our ideas about space and time. In classical physics, we think of space as a container and time as a constant flow. But in quantum mechanics, both space and time can be thought of as part of a quantum foam on very tiny scales. This foam is filled with constantly shifting shapes and tiny bubbles where space and time could behave in ways we don't fully understand. Some scientists think that at the smallest scales, space and time might not even be continuous, more like a pixelated screen than a smooth surface. When we look at large structures like galaxies and clusters, these tiny changes in space-time may be magnified, shaping the universe in ways we can't yet predict. Another cosmic mystery with a potential quantum side is dark energy. Dark energy is the name we give to the force that seems to be pushing the universe to expand faster and faster. Quantum mechanics introduces the idea that even empty space has a certain amount of energy, known as vacuum energy. While this vacuum energy is thought to be very small at the quantum scale, it might become significant on cosmic scales. Some scientists think dark energy could be a kind of vacuum energy that pushes the universe apart. If that's true, then what we see on a grand scale, the accelerating expansion of the universe, might actually be the result of quantum behavior in empty space. In addition to dark energy, cosmic inflation is another place where quantum mechanics and cosmic phenomena intersect. Right after the Big Bang, the universe underwent a rapid period of expansion, known as inflation, which shaped its current structure. During this period, tiny quantum fluctuations were stretched out across space. These fluctuations became seeds that later grew into galaxies, stars, and planets. Even though they started out at a quantum level, inflation made them large enough to shape the universe. Without these quantum fluctuations, galaxies might never have formed, and the universe would look completely different. One more concept connecting quantum mechanics and cosmic scales is the holographic principle. This principle suggests that all the information in a region of space can be thought of as being encoded on a lower dimensional boundary. Imagine if everything inside a three-dimensional area of space could be described by a hologram on its surface. This principle comes from theories about black holes, where information that falls into a black hole might be stored on its surface. Some scientists think this idea could apply to the entire universe, meaning that the three-dimensional world we experience might actually be a projection of information from a lower dimensional surface. If this is true, then quantum information could be embedded in every part of the universe, from the smallest particles to the largest galaxies. Quantum mechanics even affects how we think about the structure of the cosmos itself. According to quantum theories, particles like electrons can act as both particles and waves. On a cosmic level, this wave-like behavior might affect how matter is distributed across vast distances. If galaxies and galaxy clusters are influenced by wave-like patterns, then the layout of the universe might have a kind of quantum imprint. This pattern could explain why matter seems to be clumped together in certain ways, creating clusters, filaments, and large voids between galaxies. In addition, recent theories are exploring how quantum mechanics might create unusual cosmic structures at extremely large scales. One idea is that some regions of the universe could behave as if they are in a quantum superposition, where different possibilities overlap. This might mean that certain cosmic structures have multiple states, and the universe we observe is only one of the possible versions. Although this concept is purely theoretical, it hints at a world where quantum mechanics impacts the overall fabric of space, influencing everything from galaxy formation to the layout of the cosmos itself. In exploring quantum weirdness on cosmic scales, we see that quantum mechanics is not just a science of the small. It could be shaping the universe in ways we're only beginning to understand. By studying black holes, cosmic inflation, and the expanding universe, scientists hope to uncover how quantum mechanics influences the largest structures we know. One of the most unusual discoveries in quantum mechanics is that particles can act both like tiny objects and like waves. This idea, known as wave-particle duality, is fundamental to understanding how matter behaves at the smallest scales. In classical physics, we usually picture particles as solid points, like tiny marbles, each with a specific location and path. Waves, on the other hand, are spread out, covering an area rather than staying in one precise spot. In quantum mechanics, particles like electrons and photons blur these lines, sometimes behaving like solid objects and other times spreading out like waves. Wave-particle duality means that the same particle can display characteristics of both waves and particles depending on how we observe it. If you're observing an electron moving through space, it may behave as if it's a tiny, solid object following a specific path. But in other situations, like when it's passing through a barrier with two slits, it acts more like a wave, creating an interference pattern, a pattern that only waves can form. This shows that particles at the quantum level don't follow the same rigid definitions we're used to in everyday life. The famous double-slit experiment is often used to explain wave-particle duality. In this experiment, particles are fired one at a time toward a screen with two slits. If we don't observe which slit the particles go through, They create an interference pattern on the screen behind the slits, similar to ripples in water overlapping. This pattern suggests that each particle acts like a wave, passing through both slits at once and interfering with itself. But if we set up detectors to observe which slit each particle goes through, the interference pattern disappears, and the particles behave as if they are going through only one slit at a time, like tiny marbles. The simple act of observing the particle changes its behavior, a core feature of quantum mechanics. To make sense of this dual nature, it's helpful to look at how waves and particles behave differently in classical physics. For example, if you drop two pebbles into a pond, each pebble creates ripples or waves that spread out from where it hits the water. As these waves expand, they cross over each other, creating areas where they add up to make a bigger wave. Constructive interference, or cancel each other out. Destructive interference. This is a classic wave behavior that we can observe easily in water, sound, or light waves. Particles, however, don't create interference patterns. If you throw two marbles, each follows its own path, and they don't interfere with each other in the same way waves do. But in the quantum world, particles like electrons, photons, and even larger particles can create interference patterns. This shows that, under certain conditions, particles don't behave like tiny objects with clear positions and paths. Instead, they behave more like waves, which are spread out and create interference. The idea of wave-particle duality also applies to photons, the particles that make up light. Light was once thought to behave only as a wave, since it creates patterns like interference and diffraction, bending around corners, which are wave behaviors. However, experiments later showed that light also behaves as if it's made up of individual particles, or photons, which carry energy in tiny packets. These photons interact with matter in ways that only particles can, such as when light knocks electrons off a metal surface in a process called the photoelectric effect. This discovery helped establish that light has both wave-like and particle-like properties, depending on how it's measured or observed. One way to understand this strange behavior is to think of particles as having a wave function, a mathematical function that describes all the possible positions and states that the particle can be in. When the particle isn't being observed, its wave function spreads out, covering all these possibilities at once. In this state, the particle behaves more like a wave, able to create patterns and interfere with itself. But when we measure the particle's position, we collapse its wave function into a single state, making it act more like a small object in a specific place. This collapse of the wave function is what gives particles their dual nature, appearing as waves or particles depending on the situation. It's important to note that wave-particle duality isn't limited to photons or electrons. In fact, experiments have shown that even larger particles, like atoms and some molecules, can display this dual behavior under certain conditions. For example, scientists have conducted experiments where large molecules are made to pass through a double-slit setup, and they form an interference pattern as if they were waves. This shows that wave-particle duality is a general feature of matter at the quantum level, not just a special property of light or tiny particles. This dual nature leads to many unexpected results in quantum mechanics. Because particles can behave as waves, they don't move in straight paths with exact trajectories, as we might expect. Instead, they move in patterns that are spread out based on probabilities and can even overlap and interfere with other particles in complex ways. This behavior is part of what makes quantum mechanics so different from classical mechanics, where we expect particles to have specific locations and follow predictable paths. The implications of wave-particle duality extend into many areas of physics. For example, The behavior of electrons as both particles and waves is crucial for understanding how atoms bond to form molecules. Electrons within atoms occupy regions known as orbitals, which are areas around the nucleus where electrons are most likely to be found. These orbitals are shaped by the wave-like behavior of electrons, allowing them to occupy different energy levels and form stable arrangements in atoms and molecules. Another area affected by wave-particle duality is quantum tunneling, a process where particles pass through barriers that, according to classical physics, they shouldn't be able to cross. Since particles at the quantum level have wave-like properties, their wave functions can leak through barriers, allowing them to appear on the other side even though they lack the energy to cross directly. This phenomenon plays a role in many natural processes, including nuclear fusion in stars and some types of chemical reactions. Wave-particle duality reminds us that at the quantum scale, particles are not limited to behaving as solid objects with exact positions. Instead, they exist in a state that's both particle-like and wave-like, adapting depending on how we observe them. This strange duality is one of the fundamental principles that makes quantum mechanics so unique, showing us that nature at the smallest scales does not follow the rules we see in everyday life. The holographic principle is a fascinating concept that suggests our entire universe might be like a hologram. Now, this doesn't mean the universe is a literal hologram, like the ones we see on a credit card or a movie poster. Instead, the idea is that everything we observe in three-dimensional space, planets, stars, galaxies, even us, could be explained by information stored on a two-dimensional surface, like a boundary that holds all the instructions for the three-dimensional world we experience. This concept is rooted in the study of black holes. Black holes are regions in space where gravity is so intense that even light can't escape them. When something falls into a black hole, it's as if that object disappears into the black hole, leaving only the black hole itself. But what happens to the information about that object? In physics, information about matter and energy should never be lost, even if it's compressed into a black hole. To solve this mystery, some scientists proposed that all the information about anything falling into a black hole might actually be stored on its surface. This idea was a big step toward the holographic principle. One scientist who explored this was Leonard Susskind, a physicist who thought about how this principle could apply to the whole universe. He suggested that just as information about an object might be encoded on a black hole surface, all the information about our universe might be encoded on a two-dimensional boundary. This surface could be like a giant cosmic screen containing all the data needed to create the entire universe. This idea changes how we think about space in reality. Normally, we think of ourselves as moving through three dimensions of space: forward and backward, up and down, left and right. The holographic principle, however, says that everything we see and experience in three dimensions might be a kind of projection from a two-dimensional surface. If true, this would mean that reality is not quite what it appears to be. One place where the holographic principle seems to make sense is in theories about the early universe. Right after the Big Bang, the universe was extremely dense and hot. As it expanded, quantum fluctuations, or tiny jumps in energy, spread out and formed the seeds of galaxies and stars. Some scientists think that these fluctuations might contain clues about a hidden two-dimensional structure underlying the universe. If the holographic principle applies here, it would mean that all the complex structures we see in the universe, including galaxies, stars, and clusters, might have their origins in information from this two-dimensional layer. The idea of a holographic universe also has interesting connections to quantum mechanics. In quantum mechanics, everything exists as probabilities until observed or measured. Particles don't have fixed positions or speeds until we measure them. The holographic principle might help explain why this happens. If all information about particles is stored on a two-dimensional boundary, what we observe in 3 dimensions could be more about the way this information is projected rather than where particles actually are. This might help explain some of the unusual behaviors we see in quantum mechanics. A key example of this is in string theory, an approach that tries to describe particles not as points, but as tiny strings vibrating at different frequencies. String theory suggests that all particles, forces, and even space itself can be described by these strings. It also suggests that there might be many more dimensions than the 3 we experience. The holographic principle fits into string theory because it allows us to imagine these extra dimensions as part of the projection of the universe. Instead of thinking of extra dimensions as something we could see or touch, they might be a part of the underlying information on the two-dimensional surface. Physicists have developed mathematical models to test these ideas. The holographic principle also makes us rethink what we know about space-time itself. In our everyday lives, we think of space and time as being fixed and unchanging. We move through space and experience the flow of time. However, in quantum mechanics and theories involving gravity, space and time can stretch or warp, like fabric. In a holographic universe, space and time might be part of the projection rather than absolute things on their own. This could mean that the distances we experience in 3-dimensional space are distorted or influenced by the two-dimensional surface that holds all the information. Some scientists even wonder if this projection process could explain the mysterious dark energy that drives the universe's accelerated expansion. In laboratories, physicists are also studying holographic systems in experiments involving ultra-cold atoms. In these setups, scientists can create conditions where particles act according to certain holographic principles, which may give insights into how a holographic universe would work on a small scale. While these experiments can't directly confirm the holographic principle for the whole universe, they help scientists understand the math and physics involved. And there you have it. The quantum world is full of mysteries, from particles and forces to the very fabric of space and time. It challenges what we think we know about reality and makes us question what might be hidden in the structure of our universe. If you enjoyed diving into these mind-bending ideas, don't forget to give this video a thumbs up. And if you're ready for more deep dives into the wonders of the cosmos, hit that subscribe button and turn on notifications so you don't miss a thing. Thanks for watching, and I'll see you in the next video.